In this problem, we are given the function f of x equals x squared. We are to find a formula for a new function, call it g, whose graph is obtained from the graph of f of x after following the sequence of transformation of which there are 5. So I'm going to begin by writing down my original function, f of x equals x squared, and start with the first transformation and work my way down. It's the shift to the left 3. The general notation to shift to the left 3 is f of x plus 3. And to explain what this function notation means, in case you don't know, means literally to take the input variable, which is x in this case, and literally replace it with parentheses x plus 3. In some cases, the parentheses aren't necessary, but in this case, in fact, it is. So doing literally that, since this is the first transformation, I am changing the function, so I can no longer call it f. I'm going to name the function f sub 1, and f sub 1 will be obtained by taking the original function f and replacing x with x plus 3. So doing that, replacing x with x plus 3, this is where I proceed to do what I said, take the input variable x and replace it with parentheses x plus 3. And of course, it's still the squaring function, so this still gets squared. So later in the video, I will show the graph of this versus the new function f sub 1 and prove that it does indeed move the graph to the left 3. Moving on to step 2 here. The reflection across the y-axis, the general notation for any function to reflect about the y-axis is very similar to this, except instead of replacing x with x plus 3, you are to replace x with minus x. And again, many times it is important to use parentheses. In this particular case, it is not. So for example, doing that, moving from this function to transformation 2, I'm going to say that my second function here, f sub 2 of x, is obtained by taking the previous function, which was f sub 1, and simply, wherever I see the input variable x, I am to replace it with minus x. I will do it with parentheses just to show you what it would look like, and then argue that it's not necessary. So doing that, whenever you take x and replace it with parentheses minus x, let's see what that would look like. You'd still have the plus 3, and it would be squared. So if you have the wisdom to see ahead what this is going to look like, there really is no use for this inner set of parentheses. You could think of it as there's a positive 1 in front. If you went on to distribute it, you could, but it wouldn't change anything. So for purposes of the video, trying to keep this as clean as possible, in this particular case, I am just going to replace x with minus x and not replace it with parentheses, but there are many examples where you would have to. So this would be a y-axis reflection. Again, in the end of the video, I will show the graph of f sub 1 and f sub 2 and show that this graph is a y-axis reflection relative to f sub 1. So moving on to step 3. Step 3 is actually pretty simple. Moving a graph down, the general notation is to take a function, and to move its graph down, you simply subtract 1 on the outputs. So this is the notation for the output of f of x, and we are simply to just write down its equation, right? We're not making any changes. We're replacing x with x, if you will. No changes to the input variable, just copying the equation down and subtracting 1. So my third function, f sub 3, you could think of it as we are simply going to copy f sub 2, not change the input variable, right? This is x, and I'm leaving it x. I am simply going to copy down the previous result and then subtract 1. So that would look like this. This is the previous result. This here is f sub 2 of x, and I am to subtract 1. So let's not make that more complicated than it needs to be. Function 4, since I am supposed to apply a vertical scaling by a factor of 2, since it's a 2, since it's bigger than 1, my outputs are going to get bigger, so it does stretch the graph in the vertical direction. So the general notation for a vertical scaling is to take a function f of x, and since it's vertical, it's the output that gets multiplied by the factor, not the input. And it happens to be a factor of 2, so that'll look like this. So moving from function 3 to function 4, turns out, again, I'm not manipulating the inputs. I'm going to simply copy f sub 3, which is all of this, write it down, and multiply the entire thing by 2. So you have to try not to fall into the trap of doing this, however. Here's me copying down the previous function, that is f sub 3. Don't fall into the trap of simply multiplying by 2, because by doing so, you've only multiplied this piece here by 2 and not the entire function. So not only does this have to be multiplied by 2, but also the subtract 1. So you could think of just putting brackets here or larger parentheses. I'm gonna choose brackets. So if I did this, if I took all of f sub 3, multiplied the entire thing by 2, that would be a vertical scaling by a factor of 2, and you'll have to wait to the graphical portion of this video to see exactly what that looks like if you don't know already. So finishing off the algebraic explanation, a reflection across the x-axis is a manipulation on the output, so these tend to be easier. You're not doing a symbol swap. You're simply taking a function, and if you want its graph to reflect about the x-axis, you simply multiply it by -1. So it's not regarded as a scaling. You're not changing the size of the outputs. You're multiplying by 1, if you will. It's just you're negating the sign on the output, which reflects the graph about the x-axis. So you can think of this as my fifth and final graph. If you want, we can call this now g of x, since it'll be my final graph, or equation, that is. G of x, the fifth one, would be found by taking the previous function, which is f sub 4, and simply multiplying on the outside by a negative. So you could think of it this way. Here's me copying down f sub 4, just literally copying down the previous result. And as if this isn't convoluted enough, we're going to add this. So here's me copying it down. And if it weren't for these brackets, I'd be worried. But by putting a minus out here, because we already have the brackets, there really is no sense in putting another set. You could, it just doesn't change the result. So ordinarily, I would say copy the entire previous function. This is f sub 4 here, and then put a negative on the outside. But it just turns out that if you would distribute the negative, it would be the equivalent of just having the minus in front of the 2. So if you want to, on your own time, simplify this all out, multiply the 2 through distributive property, subtract the 1, and then multiply through by the negative, convince yourself that's the same thing as if I left those out. It'd be the same thing as if you were to expand this binomial, combine like terms, and then distribute the -2. So this is my final product. It would be very difficult if you were to graph, say, this and that, to see the progression of the transformations, but now I'm going to proceed to a graphical explanation where I move from each piece to the next. Here is the graphical explanation of the 5 transformations we did. We started with the equation y equals x squared, so you're seeing that graph. And what we did is we replaced the input variable x with parentheses x plus 3. And I claimed when you did that manipulation on the equation, that would have a subsequent transformation of the graph of a shift to the left 3 units. So graphing that, you can see that the now blue graph is a shift to the left 3 relative to the red. Because the graphing plane here gets convoluted with several graphs, I'm going to take off the red graph. Now this is what I called f sub 1 in the algebraic explanation. Moving from function 1 to function 2, applying the second transformation, we took the input variable x and replaced it with minus x, and I made the argument that that would be, in terms of graphs, a y-axis reflection. To explain what a y-axis reflection is, imagine being in kindergarten and putting blue finger paint on this piece of paper, and imagine then you were to fold the piece of paper about this vertical line. The question is, if you folded about the vertical line, where would this finger paint go? Hopefully you see that it would flop over from quadrant 2 to quadrant 1. More specifically, for example, the point -3, 0 here would get mapped over here to 3, 0. Graphing it in this pale green ugly color, in fact, you see that exactly that happens. Moving along to the next transformation, what we did was we simply copied the equation. We did not manipulate the input variable. We simply copied the previous function, you can think of that as the output, and simply put a subtract 1 at the end, and I argued that moves a function down in terms of its graph. And you can see that if you were to take the pale green color here, move it down 1, you'd get the purple graph. So let me turn this one off and move to the next transformation, for which we again did not manipulate the input variable. We simply copied the previous equation down and then multiplied 2 in front. We called that a vertical scaling by a factor of 2. And at that point in the problem, I said when we get to the graph, you'd see that that is called a vertical stretch. Some people describe that as being like a rubber band or some putty or something that you can physically stretch out. And I'm not sure that's the best explanation, but what that is if you were to take and label all the y values or all the points on the purple graph and do nothing to the inputs, leave them alone, but multiply all your outputs, the y values, by 2, you would get the points on the orange graph. And for lack of a better phrase, we call this a vertical stretch. It does look like it gets stretched out. In fact, with a vertical stretch, all points will get moved except for x-intercepts. The reason being is that the outputs, the y values of an x-intercept is 0, and when you go and you take that output of 0 and we multiply it by 2, 2 times 0 is still 0. So notice the x-intercepts don't change with a vertical scaling. The last manipulation we did was to take the previous equation, copy it down, and then simply put a negative out in front. It looks like I copied it down wrong. This was supposed to be a parenthesis here, so I need to fix this. This was supposed to be a left parenthesis here and a big right parenthesis out there. So now having done that, I argued that you could put the parentheses outside the 2, but it was equivalent to doing it this way. And I made the argument that when you do that, when you copy a function down and put multiply by a -1, notice that everything in here is getting multiplied by the negative as well as the 2. So this previous function, the entire thing is getting multiplied by -1. That reflects about the x-axis. That explanation is just like the y-axis reflection. You put finger paint on the page. So I would have orange finger paint. I would put it here. The difference is, imagine folding the piece of paper about the x-axis, the horizontal line. Where would the finger paint go? So anything on the x-axis wouldn't change, but everything else would. So this part down here, if you folded the piece of paper, that finger paint would get smudged up here. And likewise, anything above the x-axis would get flipped down below the y-axis. It's better if I just show you. So if you can imagine the orange finger paint on a piece of paper, fold that piece of paper about the x-axis here, the result would be that that finger paint would go where you see the black. Of course, it wouldn't be black, it'd still be orange, but you get the idea.